All right, so now that we have introduced the idea of pressure, let's look at the different conditions that are going to affect pressure. Now, we have a set of laws that pretty much explain each parameter's impact on pressure. And we have what's called the gas laws. Now, there's 4 of these we're going to go over. The first one we're going to talk about is called Boyles Law. Okay, and Boyles Law tells us that there's a relationship between the pressure of a pressure of a gas and the volume of the container. Okay, so pressure versus volume. Now, if you think about it, if you were to have a gas occupying a container, okay, so we'll just draw this kind of a box here, and let's have 5 particles of gas kind of just bouncing around all over the place. Okay, eventually you get to a point where there was kind of an equilibrium in terms of the frequency with which the particles hit the walls of the container. Now, imagine if that container had a wall that was kind of stuck to the side here that we could push over to the middle of the container. Okay, and when it does that, it forces those 5 particles to go all the way to that left side. Okay, so think about what's going to happen to the frequency with which they're going to hit the wall. Okay, if they're packed into a smaller space and they're moving around randomly, okay, they will hit the wall more frequently. And this is exactly what Boyle's Law tells us. It says that the pressure of a gas is going to be proportional, I should say indirectly proportional, to the volume. Okay? Now, whenever we see that little proportionality symbol, we can replace that with an equal sign followed by a constant. Now, if we rearrange this, we find that pressure is, not just pressure, pressure times volume is going to equal a constant. Now, what that constant is depends upon what gases we're talking about and what the other parameters are doing. But the important thing to recognize is that if I keep those parameters constant, the pressure times the volume under any set of conditions is going to equal the pressure times the volume in any other set of conditions. So, another way of writing this is to say that if I have some initial pressure and some initial volume, the product of the two of those will be the same as some other pressure and some other volume. Okay, of course, this has to be within the same system for this to work. Okay, but again, this allows us to basically say, hey, we know this initial pressure, we know this initial volume. What's going to happen to the pressure if I change the volume, if I increase it or if I decrease it? Okay. Now, in terms of which units to use here, technically you can use any pressure unit that you want, and you can use any volume unit that you want. Just make sure you remember that they match up. So whatever unit you use for pressure on the left side of the equation has to be the same as the one on the right. Okay, but overall, this is Boyle's Law. Now, the next law we're going to look at is called Gay-Lussac's Law. And Gay-Lussac's Law is actually one that I think that we are all empirically experienced with. And that's because Gay-Lussac's Law is going to look at the relationship between pressure and temperature. Okay? So if you go out into, during the summertime, suppose that you fill up the air in your tires, and then you notice that after the first very cold day of the year, your tire pressure sensor light comes up. Okay, does that mean that a whole bunch of air has escaped your tires? Well, it's possible, but it's a lot more likely that the pressure has gone down. And the reason for that is because the temperature is going to be related to the energy of the particles. So at higher temperatures, the gas particles are going to have greater energy, kinetic energy. Okay, which means they're going to move faster. Okay, so we increase the temperature of a gas, it's going to move faster. We decrease the temperature, it's going to move slower. The faster the gas moves, the more frequently it's going to collide with the walls of its container. The slower it is, the less frequently. Okay, so what we would expect then is that an increase in temperature will lead to an increase in pressure. And if that's the case, then we can say that pressure is directly proportional to temperature. And again, we can rewrite this as pressure is equal to some constant times the temperature, which means the pressure over the temperature, okay, for any set of conditions here is going to be a constant. Okay, and just like we saw with Boyles Law, we can rewrite this as pressure over temperature under some initial set of conditions is going to be equal to the pressure times the temperature. Divided by the temperature under a new set of conditions. Again, what we can do with this is say, hey, here's the pressure at this particular temperature. What's going to happen to the pressure when we change the temperature to, say, this other number? Okay. Now, in terms of units here, again, for pressure, we can still get away with using either millimeters of mercury or atmospheres, but temperatures can only be in one unit. Okay, and that's going to be units of Kelvin. You can't use degrees Celsius. You can't use Fahrenheit. And the big reason for that is because both Celsius and Fahrenheit allow for negative temperatures, which means it's possible you can wind up calculating a negative pressure, which it doesn't make any sense mathematically or in terms of reality. All right, so that's Gay-Lussac's law. Okay, now before we get to the next law, one important thing that I want to mention here is that when we're looking at these two gas laws that I've just shown you, we have Gay-Lussac's law and Boyles Law. In Boyles Law, we talk about pressure and volume, but we're making an important assumption when we use this equation. And the assumption is that the temperature is constant. Okay, and we're also assuming that no particles of the gas are being allowed to escape or no new ones are being introduced. So we can say the number of moles is also constant. Now, when we look at Gay-Lussac's law, we're talking about pressure and temperature. Okay, there we're making the assumption that the volume is constant. Okay, and again, we're also saying that there's no escape or introduction of new molecules of the gas, so the number of moles is also constant. Now, the last two laws that we're going to look at are not going to have pressure specifically listed or shown in the equation, but they are going to rely on pressure being held constant. Okay, so the first, or I should say the third, gas law we're going to look at here is called Charles' Law. And Charles' law is going to look at the relationship between volume and temperature. All right. And again, this is assuming that pressure is going to be constant. So pressure is constant. And so is the number of moles. Okay, then if we assume that those things are being held constant, then it's not too surprising to see that as we increase the temperature of a gas, in order for the pressure to remain constant, the volume of that container needs to increase. Okay, so what we find here is that the volume of a gas is going to be directly proportional to its temperature. Temperature goes up, volume goes up. Temperature goes down, volume goes down. Okay, we could reformulate this as B equals some constant times the temperature. Okay, or V over T is equal to K. So Charles' law has this form, where we have V1 over T1 equals V2 over T2. And what we can say here is that we can use this equation to make predictions about what would happen to the volume of a gas if we were to change the temperature from one temperature to another. Okay, and just like we saw before when we were talking about Goulds Law, these temperatures have to be in Kelvin. The volumes can be anything you want, provided that they're the same units on either side of the equation, but the temperatures absolutely must be in Kelvin. Otherwise, you could potentially get an answer that gives you a negative volume, which again doesn't make any sense. All right, and the last gas law that we're going to look at is called Avogadros Law. Okay, the same guy that they named Avogadros number after. And Avogadros Law is going to relate the volume of a gas to the number of moles of the gas present. Okay, and from here on out, I'm going to be using the letter N to symbolize moles. Okay, now here this is probably the most intuitive of all the gas laws. I mean, if you've blown up a balloon, you know that the balloon is going to get bigger as you put more air into it. So when you're blowing into a balloon, what you're actually doing is adding particles of a gas. And if you were to let air out of the balloon, you're going to see the volume of the balloon shrink down. All right, so mathematically we can show this as the volume of a gas is going to be proportional to the number of moles, okay, which means volume is going to equal some constant times the number of moles, or volume over the number of moles equals a constant value. Okay, and again, we're dealing with some assumptions here. We're assuming that we have pressure staying constant, and temperature staying constant. Okay, so we can write Avogadros law as V1 over N1 equals V2 over N2. In other words, if pressure and temperature are held constant, then any change in the number of moles will have to result in the change of the volume of the gas. All right, so that's Avogadros law. And here we're dealing with moles, so moles are moles. You can't really deal with any other unit there. And then the volume, it doesn't matter what you use, again, so long as you have the same units on both sides of the equation. Now, all these laws that I've shown you have all depended upon certain assumptions about some properties being held constant. But what if you don't have a system where it's just one thing being changed? What if multiple things are changing? Well, that's when we use the combined gas law. Okay, the combined gas law kind of puts all this stuff together. What we wind up with is P1 V1 over N1 T1 equals P2 V2 over N2 T2. Okay, and this allows us to say, all right, here's this gas that we're going to increase its volume and lower its temperature. What's going to happen to the pressure? Okay, or how many moles of a gas do I need to add to something to get the pressure to go up to some value based upon all these other factors here. Okay, so this can be very useful. And it's also important for us to recognize that this arises from the fact that we can say that pressure times volume divided by the number of moles times the temperature is a constant. Okay, and that constant that we're talking about here is given a special letter because it's used so often. It's called the gas constant. Okay, and that equals 0.0821 liter atmospheres per mole Kelvin. Okay, and then we can rearrange this into PV equals nRT. Okay, and this is our ideal gas equation. In the next video, that's what we're going to cover.